Hello, my name is Hwang, a researcher in the Visual Cognition Lab at KAIST, and I'll be presenting my paper, Looking but Not Focusing, Defining Gaze-Based Indices of Attention Lapses and Classifying Attentional States. To start, what are attention lapses? We experience every day that even when we try so hard to focus, we sometimes deviate toward a unrelated thought or daydream. For example, what should I have for lunch? Our attention fluctuates in its level of focus, and moments of zoned out states are called attention lapses. Attention lapses or zoning out may seem harmless, but it could have dire consequences from diminished learning to increased risk of accidents. Thus, defining and detecting the moments of attention lapses are crucial. One of the most popular methods of classifying attentional state is the self-report method, which includes mid-test probes to report the current state of mind. Although this method is a fail-safe way to detect internal attentional fluctuation, it is not suitable for detecting unnoticed instances or contexts with high sensitivity to time. Moreover, as it is dependent on verbal reports, it lacks the accessibility for users such as children or disabled. Thus, there is a need for a nonverbal identifier of attentional lapses with accessible data. Another popular method of attentional state classification is the post-experiment method based on the behavioral data of the users. Based on the variability of the response time, the state of attention is defined on a trial-based frequency. As this method can define attention lapses with high temporal resolution, it is often coupled with data such as fMRI or EEG to define the biomarkers of attention lapses. Although these methods showed intrinsic cognitive process with high relevance, it lacks the ecological validity in real-world usage as the indices are susceptible to noise and the data is hard to access for larger domains. Therefore, this study focused on the gaze data. Traditionally, the eye tracker was an expensive equipment that was mostly used in laboratories. As time passed, the access to gaze data have increased, and now we have multiple devices with embedded eye trackers or AI-based methods to extract eye tracking data from simple frontal cameras. So the objective of this research was to make use of this abundant gaze data and use it to define the state of attention lapses. We first identified the indices of zoning out based on the gaze data and evaluated their predictive properties through outcomes of machine learning models. One of the key challenges of using eye tracking data was how to differentiate between looking with or without focus. As the local fixation output would show the same data, despite it being done with different levels of attention. So we focused on how they looked differently rather than where they looked, focusing on the reactive ocular features and the global features rather than the local features such as fixation location. This study combined the GRASS-CPT paradigm commonly used in attention fluctuation studies and combined it with the search task paradigm to encourage active eye movement. The attentional state was defined based on the response time variability, and the trial was split into target and no target conditions. The trials always contained two color and shape distractors that share the respective features with the target, and no target condition had additional distractor of either color or shape. This is how the experiment was displayed to the participants. First, a target is shown. This would be the target for this block. And the search arrays appeared and disappeared continuously, and the participants had to respond whether the target was present or not present by pressing the keyboard buttons. While the responses were collected, the simultaneous gaze data was also collected with the embedded eye tracker in Vipro Eye. Total of 31 participants participated in the experiment. For defining the attentional state, we used the response time of the correct commission trials. And the variance time course was computed by using the difference between the mean of the quartile, which was then z-scored. The variance time course was then smoothed using a Gaussian kernel. Finally, the trials below the median VTC with low response time variance were defined as zone-in state, and the trials above the median VTC with high variance were defined as the zone-out states. All the data was analyzed with 2x2 repeated measures ANOVA. The behavioral results showed that the response time significantly slowed down when in zone-out state and when target is not present. The accuracy rate was lower for no target trials, but no difference was shown between attentional states. This result indicates that attentional lapses tend to slow down response time without affecting accuracy. For reactive ocular features, we saw the difference between the stimulus onset to the first ocular reaction to see the initiation of search. The results show that the overall ocular reaction slows down when zoned out, and when zoned in, saccade reaction was not dependent on the presence of target, as opposed to when the participant was zoned out. Moreover, when the target was present, the saccade reaction slowed down when zoned out. Next, we wanted to see the relation with the behavioral response. So we analyzed the latency between the ocular reaction to the response. The results showed that when the target was absent, the latency increased as they needed to ensure its absence. And this difference was more pronounced when in zone-in state. And also when zoned out, the saccadic reaction to response was longer. From this, we can imply that both target presence and being in the zone significantly impact the latency from search initiation to response. For global gaze features, only the saccade amplitude showed the difference according to the attentional state, and rest only showed the condition effect. The analysis showed that the participants showed larger saccade amplitude when zoned in, and the post-hoc of the interaction effect showed that there was a larger saccade amplitude when zoned in only when the target was absent. From this, we can infer that the attentional state also affects the dynamics of visual exploration, especially when target was absent. Furthermore, to examine how the gaze indices identified in this study influence the prediction of attentional states, we constructed 3 datasets. First was all the gaze indices analyzed in this experiment. Second was the gaze indices that showed significant results with zone. And third was a dataset excluding those with significant zone effect. Additionally, we compared the datasets containing only the gaze data with those that included the behavioral data, resulting in a total of 6 datasets. Then, these datasets were evaluated by trying the models both within individuals and across participants. For user-dependent models, we split the train test data within each participant, using 70% of the data for training and evaluating the model on the remaining 30%. For user-independent models, we employed the leave one group out method, where one participant's data was excluded during training, and the model was tested on the individual using the data from the remaining participants. We tested various machine learning models, including logistic regression, random forest, SVM, and XGBoost. First, for the user-dependent models, all 4 machine learning models showed significantly higher classification accuracy when trained on significant gaze indices identified in this study, compared to models that excluded them. Moreover, they also outperformed models trained on the all-feature dataset, including both significant and non-significant indices. In particular, logistic regression achieved an accuracy of 64.7% when using only gaze data, and XGBoost with 73.6% when behavioral data was included. These results demonstrate that the gaze tracking indicators defined in the study substantially enhanced the performance of classification models. A similar pattern was observed in the user-independent models. Models trained only on the significant gaze indices outperformed those trained on datasets that excluded these indices, as well as those using the entire dataset. This trend held even when the behavioral data was included. Notably, when using only the gaze data, the SVM model achieved an accuracy of 71.4%, and combining gaze data with reaction time, the accuracy increased to 79.3%. These findings provide strong evidence that the gaze indices identified in this study effectively represent attention levels. Through this study, we confirmed that the attentional states are reflected in the gaze data, and we have defined more universal and applicable gaze-based indices by focusing on eye movements rather than localized attention. This approach allows for broad application potential beyond the task-specific settings. Furthermore, the identification of gaze features that significantly enhance the model performance highlights the importance of preliminary validation experiments and interdisciplinary collaboration. Lastly, the findings of this study can be applied in various contexts, including development of learning aid by detecting the moments of attention lapses for students and providing necessary cues, or hazard prevention application for drivers by detecting zoned out states and providing warnings. Thank you for your attention, and please check my paper for further details.